for watching. I'm Dimitrii, software engineer at Red Hat and Postgres contributor, and today we're going to talk about databases performance and benchmarking. And we're going to start right away with an example. So what usually happens when we would like to understand the database performance? Usually we just pick up some off-the-shelf existing benchmarking tool. Fortunately, there are plenty of those nowadays. We run this tool against our database, we've got some numbers, we put those numbers into report and everything is fine. Now at some point we would like to reproduce the data and we suddenly realize, oh crap, the data, the numbers are quite different now. Something was wrong, we are going to investigate, we'll probably find out that there was some misconfiguration or maybe there was some noise in the system when you were running and you were conducting an experiment in the first place. So you're going to fix this, you're going to correct your numbers and everything is fine, except that now we've got a certain problem. We do not trust those numbers anymore. And this is what we're going to talk about. We're trying to understand how to boost your confidence about benchmark data and how to analyze this data correctly. Now, before we jump into this, it's important to establish a model, how to think about benchmarking in the first place. I appreciate obviously that everybody thinks differently, so this is just an example that I find particularly useful. I prefer to think about databases as a complex systems where you can describe their state using a phase space, like it's called in mathematics, or design space from statistics, where essentially you've got some set of dimensions and every single point of the space describes the state of your database at some particular moment in time. As an example, you can take a look at this slide. You can see a Lorentz attractor and its phase space, and this is something that I've got in mind. Now, you may ask, what are the dimensions of this space for a database evaluation, right? There's quite a lot of them, actually, and obviously, for example, a database configuration is definitely a part of this dimension set, because you're configuring something, you're changing database behavior. At the same time, all the hardware limitations are also, of course, a part of this dimension set, because your database is going to perform differently if it, for example, if it's got not enough memory. Interestingly enough, the input for our model, so the workload we're generating, is also part of this set, because your database is going to perform differently when it receives, for example, 1 query per minute versus when it receives hundreds of thousands of queries per second. And the output of our model, all the latencies of bandwidth or whatever, it's also going to be a part of this dimension set. So, having said that, we are ready to discover a very interesting property of benchmarking. So usually when we're exploring our system, we have some prior knowledge and we would like to extend this knowledge. But it's always the case that there is some amount of unknown factors coming in. So either we don't really know how certain factors are going to affect our performance, or maybe there are even certain things that we're not aware about at all. And this duality is actually very important for benchmarking process, because it also produces another duality, particular knowledge versus common knowledge. It's very important to apply both of those skills. It's very important, for example, to understand the domain clearly. It's very important to understand how your database works. Because, of course, without having this knowledge, you'll not get away with understanding your data. But at the same time, it's important to complement this with a common knowledge, with, for example, knowledge about statistical method, about how to analyze this data. You cannot get away without one or another one in any kind of way. That's why the following slides are actually divided into two categories, and we're going to start with the specific details about Postgres and how and what we need to keep in mind and not screw your performance evaluation of a database. Now, obviously, most of the time what happens is that there are simply just a misconfiguration that happens because, there are quite a lot of knobs that you can configure for your database, and not all of them are so clear what to do with them and how to configure them. Just from top of my head, I've put a couple of those on the slide. Interestingly enough, there's a very interesting paper from Autotune folks when they're stating that for them and their algorithms they're using for machine learning, they have found out that the most performance win they've got by tuning only two parameters, shared buffers and Maxwell size. which means that those two are probably arguably the most important in this context, but nevertheless, the rest of them are also valuable in certain situations. Work mem, checkpoints, you name it. Now, the situation is that you probably cannot get away by configuring the database alone. Most of the time you have to think about the underlying platform as well. Like, for example, in this case, we have some configuration for Linux. And yeah, if you would like to get a reasonable performance, you need to understand how many huge pages you've got, how file cache is working, what is the I/O scheduler, and so on and so forth. Now, it sometimes comes as a surprise, especially for those folks who are doing performance analysis before for stateless systems, that it's important to appreciate the temporal properties of your system, so temporal properties of the database, because certain effects are kicking in only after some time. On the slide I've put, for example, a default configuration for auto vacuum, because auto vacuum is certainly one of those things that is important to understand whether or not you're actually capturing this in your test. You don't have to like explicitly configure it, although it may be useful, but at least you need to understand whether or not those effects are included within the time frame of your evaluation, whether it's auto vacuum, data bloat, checkpoints, whatever, because all of them are obviously going to be important in the long run. Now, another very interesting detail is that the log generator might be as important as the database itself sometimes. The thing is that there could be the case that the log generator is the bottleneck in your system, and your log generator is just not able to put database under enough pressure to actually understand its performance. And that's why it's important to monitor both of those to see, like, utilizations on both sides and so on. Especially PGBench has actually a negative history of being a bottleneck in certain situations. But there's more to this story actually. And this more is coming from a queuing theory. So usually when we're talking about databases in production, we refer to them as an open systems, which means that we just got some amount of incoming queries with a certain rate, and we've got some replies and like responses to those queries. This is again what's called an open system. The thing is that when we're doing benchmarking, we're actually doing something different. Most of the time, workload generators are firing queries, and then they're waiting for those queries to finish to fire another round. So we've got a limited amount of queries in the loop, and this is what is called in queuing theory a closed system. And the point is that there is an important distinction between those two, especially when it comes to tail latency. So they are simply behaving a little bit differently, and no reason to freak out. You still could use those tools, but it's just important to realize that sometimes you're just evaluating something a little bit different. And I think out of those tools, only Benchbase was allowing you to run in some sort of a mode when it's using Poisson distribution to actually generate those, like a Poisson process to generate those queries and simulate sort of an open system. Yep, so now we've got some sort of a high-level overview of various details about Postgres and how to benchmark it. So let's go to the unknown part. Let's go to the statistics and how to tackle various problems with the data analysis using statistical methods. The interesting part here is that the whole idea about using statistics for experimentation is actually not new. It's been there for quite a while for various natural sciences like biology, physics, chemistry, you name it. For example, here on the slide you can see a quote from a paper that introduced quite well-known student t-test, which is a main workhorse for many data analysis methods up to until now as well. And you see that this article is like more than 100 years old. So this is a well-established area. And there is some tooling, a very powerful tooling being developed most of the time when we're using this tool, and that's what you could see. So we're just talking about the data as a random variables. They have some population with some certain metrics, whether it's a central tendency or variation. Then we're doing benchmarking. We sample those populations. We get some statistics like some averages, some estimation of variances, and so on. And then using this data, we perform t-tests to understand whether or not some sets of data differ in a significant way. You don't have to remember those formulas, of course. First of all, because it's not really important, and the second, because most of the time they're going to be implemented in whatever data processing framework you're using, whether it's a SciPy, R, or whatever. What's important here, though, is to understand their limitations, because there is one significant limitation. All this tooling is being developed under the assumption for the random variables. They're supposed to be normally distributed, independent, identical random variables. And, well, it turns out it's a very strong assumption. So it's okay for the, again, natural sciences. So, for example, in the physics or biology, almost all the processes that people are dealing with, they are normally distributed. Now, in computer science, unfortunately, we've got a problem. Most of the time when we're talking about processes in computer science, they are actually not normally distributed, and rather they have a very strong skew to the side and a very long tail. So you can see on this slide an example of such distributions. The blue line represents your normal distribution. That's what we have to get when I would like to use the tooling from before. And the red one represents what we usually have to deal with from computer science. You see the pretty much long tail and rather a strong skew to the side. The intuition behind this is very straightforward. Since everything in computer science is essentially a queue, there is a sort of a happy path for your query to go through your system, and everything else could happen, all the deviations that happens to it could be only make things worse. It's either could be a congestion or lack of resources or something. That's why we've got this long tail. What does it mean for us at the end? It means, unfortunately, that strictly speaking, we are not allowed use this powerful tool in I've shown before for analyzing of our performance evaluation data. We're just going to, strictly speaking, we're not allowed to do this, we're just going to get the wrong results. So, what should we do? Fortunately for us, there is some set of methods being developed, again, exactly for this type of situations, for non-normal distributions. They're a little bit more complicated probably, but nevertheless rather straightforward again. So you may want to use, for example, more robust statistics, like you want to use median, quantiles. You want to, for example, think about outliers in terms of interquantile range and so on. And you can, for example, replace t-test with a Mann-Whitney test. Now, an interesting detail to this, a little bit controversial maybe, but nevertheless, you might be lucky actually, and sometimes you can have a data set that could be not necessarily normally distributed, but could be reasonably approximated with a normal distribution, and then you could use all this powerful tooling I was showing before. An example of this shown in the, for example, book Statistics for Experimenters and projects like Hunter, for example, they're showing that it could work in certain contexts. So you just need to be aware that sometimes it could be the case that you could use those tools, but generally speaking, you have to understand that normality is not something that you could assume just right away. And now a couple of interesting practical questions. Frequently I see people asking, how many runs do I need to perform to fit my data into a reasonable confidence interval? Generally speaking, it's rather a complicated question, depends on many things, but there is a very interesting research I found where people are trying to analyze this question based purely on the hardware noise. So how many runs do you need to perform based on the hardware noise to get some reasonable data? They have introduced a function E that says like, for random variable X, how many runs do you need to do to get a 95 confidence interval where the value lies within 1% of median. And they've got a set of interesting results that you could use as sort of a ballpark numbers, like a sort of an expectations, what to expect from your system based purely on the hardware noise. They found, for example, that when you've got a coefficient of variance very low, like so your data is very stable, 0.3%, you don't have to even bother that much. You can just get 10 runs and be fine with this. If your coefficient of variance is growing to 9%, so the data is becoming more volatile, you have to, of course, put more efforts. You have to run 200-something runs, so it's a little bit more, but nevertheless, it's something like a couple of hundred of runs. And I think for storage noise, they're also getting like a 600 or something. So it's something to keep in mind approximately what to expect from the system. Now another very interesting question, and it was actually sort of an inspirational question for this talk. Some time ago, Mark Callaghan was asking, like purely from statistical perspective, what makes sense more? Does it make sense more to run a longer test, longer benchmark? Or does it make sense to run a set of shorter benchmarks? The question is very interesting and pretty much depends on the context, of course, so usually you cannot really compare those. But at the same time, there is a very interesting result, again coming from queuing theory, that says both of those are actually going to be equivalent if we're talking about an ergodic system. By ergodic system, I mean here a system that repeats its own history, so the oldest history is not really important for the system. Now, obviously, it's not very reasonable for databases to assume to get this assumption. But nevertheless, I can imagine that if you could configure your benchmark to clean up data reasonably and to configure vacuum reasonably, then maybe you could approximate your database and say that it's approximately an ergodic system. Now, final thoughts. Probably the main takeaway I would like for you to be is that benchmarking is not necessarily just to dry statistics and numbers and all this stuff. Benchmarking is actually quite interesting. Benchmarking is exploring. It's learning something new about your system. It's very fascinating to see all this stuff. And a second point is that it's very important to appreciate this duality between known versus unknown and common versus particular, up to the point that you sometimes need to catch up with skills from one area or another one, or you may, for example, use different tools to address one problem or another one. I did not put that many details into this slide, but there are, for example, very interesting things what you could do with, for example, unknown things that you have no idea about, what you could do randomized testing or something like this. And the last point, I have not called it out explicitly, but you may see this throughout the slides, that you could use statistics not necessarily only as a method to boost your confidence, but you also could use it as a sort of a language to be able to deliver and convey your ideas more clearly to other folks, to make everybody understand what you mean by this set of data and how this data looks like. So yeah, that's pretty much it. Thanks everyone.